All right, so in this video tutorial, we're going to learn how to create flood risk map in GIS environment, and also we would like to become familiar with hydrology extension in ArcGIS environments. So let's assume that based on the opinion of experts, 5 factors should be considered for generating flood risk map. In the previous lab, we obtained the administrative boundaries as well as land cover, digital elevation model, and also we derived the slope from digital elevation model in the study area, which was Cuyahoga County, Ohio. So you can find that video in the description, and you can also notice where you can locate this kind of information. According to the experts, so these are the 5 factors, and also these are the weights or importance of the factors for generating flood risk map. As you can see, precipitation has the highest importance, and among the factors, elevation is the least important factor in generating flood risk map. So in ArcGIS environment, let's add Cuyahoga County GIS flood mapping. Okay, so we have county of the Cuyahoga County. Let me make this hollow, and also I'm gonna add the use a red color for the boundary of the study area. So that's the Cuyahoga County administrative boundary. The next one was land cover type that we talked about, that each if you load this, each pixel value shows a specific type of land cover. I think the resolution was 30-meter spatial resolution. Another factor was digital elevation model, or DEM. When you add that, each pixel shows elevation for that specific location, and again, the spatial resolution was 30-meter, and the elevation varies from 168 meters to 391 meters in the study area. And also we derived slope from the digital elevation model, and as you can see, a slope changes from 0 to 41 degree, that we already talked about that in the previous lab, that how we can drive a slope from the digital elevation model. The next factor is precipitation, but first let's from customize menu go to the extension and then check spatial analyst on. And after that, and also you have to limit the process. We want to limit all of the calculations to this study area. So from geoprocessing and then environments. So if you go to the processing extent, we're gonna set the extent as same as county layer, and also the cell size as digital elevation model. So same as slope or digital elevation model, and also we want to use the county as the mask. Okay, so click OK. So we don't want to do any calculation outside of the study area. Okay, so regarding precipitation, we can get the precipitation information from WordClimb website. If you go to the wordclimb.org and then click on downloads, so WordClimb provides relatively high spatial resolution global weather and climate data. Okay, and it is extensively used in spatial modeling. So we can get the historical information of the climate or weather conditions. So if you click on historical, and after that, this website provides the monthly climate data for minimum, mean, maximum temperature, precipitation, solar radiation, and so on. Okay, so here we have the variables, and also here we have the resolution. So the best resolution is 32nd, which is 1 square kilometer. So I'm gonna download the precipitation with 32nd or 1 kilometer spatial resolution, which provides the data. And as you can see, the values are between 1 to 12, so it's a monthly information. So let me click on this one and download it. So there's gonna be 12 raster grid, and we're gonna focus on March, because most of the floods normally occur during March because of the after snow melts and because of the rainfall. So I'm gonna focus on only for the March months and consider it as the precipitation. So if you open up this file, so I already have unzipped this file. So you'll notice that if you click on README, so it shows that they represent average monthly climate data from this period of time, okay? So we have the value from months 1, 2, 3, 4, and so on. So we're gonna focus on month 3, which is March, and the data are for the entire world, okay? So we have to clip it with our study area. So let me click on add data and then connect to folder of the downloads. And then here I'm gonna select the month 3 and then add. So you can see it's for the entire world. If I click on full extent, it's for the entire world, but I'm gonna just focus on Cuyahoga County. So let me zoom to this layer. I have to clip this big raster with the Cuyahoga County. Okay, so if I type clip here, clip data management. So input raster is going to be your precipitation for March, and the output extent is going to be for county. And after that, we want to use input feature for clipping geometry. Okay, so if it's checked, the geometry of the selected feature is used to clip. So it's going to be for the Cuyahoga County. So we don't need to convert this to no data to this value. And I'm gonna save this as PRC precipitation. So that's the precipitation for Cuyahoga County, and maintain clip extent and then click OK. So as you can see here, we have the precipitation, but the resolution is not perfect. That's one of the limitation of this data, that when you have the data for the entire world, the spatial resolution is 1 kilometer, is not 30 meter like the other variables that we have. But so that's going to be our precipitation layer. So I'm going to remove this one and only consider this as precipitation. So before focusing on the next variable, which was proximity to streams or channels, let's look at the hillshade of the study area. So what is hillshade? So let me turn all layer off. So the hillshade provides a more clear picture of topography, because it mimics the sun effects on hills and canyons. Okay, so if you type hillshade and Hillshade Spatial Analyst, so your raster input is going to be your digital elevation model. The output is going to be your hillshade. And so these two, azimuth and altitude, are for lightning sources and optional information. So I'm going to accept the default values for the hillshade. And after that, I'm going to click OK. All right, so now here is the hillshade. If you zoom in, you can see the details of landscape. So it's like almost 3D image. Okay, so here you can see the variations of the landscape. But if you want to see better the variations in the hillshade, if you right click on hillshade, properties, go to the symbology tab and stretch it based on standard deviation and then apply OK. You can have a more clear picture of the topography. Okay, so here probably we have some depressions, we have some channels, so you can better see the topography changes of the study area. So let me add the land cover on top of this layer. So we had land cover here. I'm gonna move it on top of the hillshade here. And then what I'm gonna do is I'm going to increase the transparency of the land cover. Okay, so right click on that, properties, go to display, and then for transparency, I'm gonna increase it to 40% and then apply and OK. So here you can So you can see Landcover, 3D Landcover map, kind of. So this map is called shaded relief map, is a 3D, almost 3D form of the land cover. So this is how the landscape look like. So we don't need this hillshade for our analysis, but we just wanted to have a representation of the landscape, so we can remove it from our analysis. Okay, so let me remove the hillshades. Okay, so the next step, so we have the elevation, slope, land use, precipitation. The last one is proximity to streams, right? So we want to extract streams from digital elevation model, but there are multiple steps that we need to take to extract the streams or channels from digital elevation model. Okay, so let me remove all layers. We can add them later. So let me select all layers and then remove it. Okay, so I'm gonna just keep the digital elevation model. Okay, so in your digital elevation model, the first step is that we have to fill the digital elevation model. And what does it mean? So in your digital elevation model, there might be some sinks or pits that are pixels that are lower than surrounding cells. Okay, so here, if you look at this one, so if this is the digital elevation model and each cell represent elevation, so some pixels are significantly lower than surrounding cells. Okay, so the problem of sink is water will trap in these cells. Okay, and these spurious sinks are found in most digital elevation model products because of the small random errors in data collection. And the fill function, as we can see, helps us to modify the elevation value to eliminate these problems by filling the artificial sinks in the digital elevation model. Okay, so we need to fill the digital elevation model, and to do that, if you go to the Arc toolbox here, and then from Arc toolbox, if you scroll down and find spatial analyst, and then the hydrology extension, expand the hydrology, and then here we're going to focus on this hydrology extension. Okay, so the first operation is fill, and the fill, the input is going to be your digital elevation model, and the output is going to be fill. Okay, I'm just going to call this fill. And Z limit, what is Z limit? Because in order to differentiate natural and artificial sink. Okay, sometimes you have natural, you have something, but sometimes you have sinks because of the errors. It's an artificial thing. So we need to set up a threshold value for errors. Under, for example, if I put the value of 10, the values that are under 10 is going to be filled, okay? And above that is considered a natural sink and should not be filled. And here also explains that if the difference in Z values between a sink and its pour point is greater than the Z limit, the sink will not be filled, okay? And the value for Z limit must be greater than 0. We don't have any natural sink, so I'm gonna click on OK and have this convert this digital elevation model to fill it. Okay, so as you can see, so the values for digital elevation model start from 168 to 391, but here after removing the sink, now it starts from 173. So in summary, fill function corrects your digital elevation model. Okay, so sometimes fill is called depression-less digital elevation model. Okay, so it's a corrected version of digital elevation model, and there is subtle difference between the digital elevation model and fill, but we're gonna use fill for the following steps. So the next step is that we need to create flow direction raster. And flow direction raster means if rainfall falls on the surface, how would it flow, okay? And we assume that water flows following the slope direction. In other words, the direction of steepest descent. For instance, in this image, there are these are the pixel values of digital elevation. So these are the pixel values of digital elevation model. Okay, so from 78, so which pixel or the neighbor pixel has the lowest value? So it's obviously 67. And you can see that the water flows in this direction, okay? From the second one, for the second one, 72, which pixel value causes the steepest slope? And definitely 56, right? So it's going to be in this direction. So that's why you can see flow direction is in this direction. And for 69, it's going to be for 49 is the causes deepest value. For example, 58, this one has the lowest value. So it's in the downward direction, okay? So this is our flow direction, but how computer cannot understand the direction, can understand only the numbers, right? So in order to recode it, we have to use this value. So if it's in this direction, we recode it with 2. So 2, 2, 2. If it's in the southward direction, we recode it with 4. If it's in this direction, we record it with 8, and so on. Okay, so this is going to be so flow direction, it creates a matrix of numbers, but the numbers have a meaning. Okay, so for example, 128 means that the direction is for the northeast. Direction of the flow direction is in the northeast for this specific cell. So how we can create flow direction? So we're going to create flow direction based on the field digital elevation model. Okay. So again, from hydrology, flow direction, your surface raster is going to be your field, and the output raster is going to be flow. So I'm going to call it flow DIR, flow direction. And we don't want to force the edge cell to flow outward. And if, because in the edges, the errors are very high and we don't want to involve them in our calculation, okay, which is the default value if it's unchecked. So, and if it's checked, all cells at the edge of the surface raster will flow outward from the surface raster, and we don't want that, right? And the technique for flow direction type is D8, is the thing that I just explained it, okay? Assign a flow direction based on the flow method, and this method assigns flow direction to the steepest downslope neighbor, and which is the default value. So I'm gonna select D8 and click on OK. So it creates the flow direction and the values, as you can see, 1, 2, 4, 8, 16, 32, and so on, which I explained what does it mean. So after having the flow direction from the fill raster, the next step is to find the flow accumulation. Flow accumulation counts the amount of water or upstream cells that flow into a pixel or downslope cell. So in other words, what is the gain of each pixel, okay? So from small streams to large streams and from large stream to rivers, okay? So to create flow accumulation, we have to use flow direction, okay? So the input for to create the flow accumulation is flow direction. And for example, for this one, how many unit of water flow into this cell? So definitely 1 unit is flowing in this cell, right? That's why it is 1. So how many unit of water flow in this cell? 0. Okay. But how many unit of water flow in this cell? So this is going to be for this cell. It's going to be 1, 2, and 3, right? So that's why it is 3. So why this pixel gets the value of 7? 1, 2, 3 pixels or unit of water flow in this cell, right? And another thing is that they already have the values. They already have the value of 1, 3, and 0. So it's going to be 1 plus 2, 1 plus 1 plus 1 is 3, plus 1 is 4, plus 3 is 7, plus 0 is 7. That's why this cell gets the value of 7. So keep in mind that each contributing cell has a gain from others and also from rainfall. So that's how the flow accumulation can be calculated from the flow direction, okay? So again, from ArcMap, if you click on flow accumulation, so the input is going to be your flow direction raster. So it's going to be flow direction raster. The output is going to be flow ACC, flow accumulation. So we don't want to apply weight to each cell, and the result is based only on the number of cells that flow into that specific cell, okay? So we accept the other, so for example, flow direction type is D8 and so on. So we accept the other default settings and click OK. All right, so here is the result of flow accumulation. So the pixel values, if you use identify button here, so the pixel values, for example, here is 0, here is 29, here is 0, 38. The pixel values shows the number of cell upstream that flow in that cell that we just discussed, okay? So the cells with high flow accumulations should be in lower elevations, such as in valleys or drainage channels, okay? So this image is kind of very dark, but you may see the streams, right? You can see the streams. But let me change the symbology of this layer. So if I go to the properties of the flow accumulation symbology, and here stretch it based on the standard deviation, and then apply an OK. So here you can better see the channel stream of streams or channels based on the digital elevation model, okay? So as you can see, some streams are main, which have the higher values of the flow accumulation, and some of them are not main channels, okay? So we're gonna focus on most on the main channels or main streams. Another thing is that you can compare these streams with the hillshade that we just created. So if you look at the hillshade and add it here, so you can see that. So it's kind of so this flow accumulation is kind of identified the hillshade, right? So the channels or streams that are visible from the hillshade. So let me remove this hillshade, and we're going to focus on this flow accumulation raster grid. We would like to extract the stream channel from this raster grid. And if the cell value is greater than a threshold, we're going to assign it to a value of 1, which because it shows the mainstream. And if the cell value is not greater than the threshold, we have to assign it to no data. Okay, so it's going to be 1 or just a stream or no data. And a rule of thumb for a stream threshold is that the threshold is 1% of maximum flow accumulation. Okay, so the maximum flow accumulation is 438. So the threshold that I'm gonna set is like 4,400. Okay, so it's 1% of the maximum flow accumulation. So I'm gonna reclassify this raster. So if I type reclassify into 2 classes. So for the flow accumulation, I'm gonna reclassify it into 2 classes. The value is gonna be 4,400, and anything after that is gonna be 1. So this is gonna be no data, and here make sure that D is capital, and anything above the threshold is gonna be 1 because it shows the main streams. So these are the flow accumulation, and the output is gonna be our streams. Okay, so this is how we can extract the streams from the digital elevation model and change missing values to no data. So let's click OK, turn on layer off, and here you can see that. So these are the streams that we detected that from the digital elevation model. Okay, so I just wanted to show you the application of hydrology extension. So you can also delineate watershed and also use it in utility network in the future. All right, so we found the streams from digital elevation model based on multiple steps that we took, but we need to find the proximity to these streams or channels, okay? And the function that you know is Euclidean distance, okay? So if you type Euclidean and Euclidean distance spatial analysis, so we're gonna find the distance to these streams, okay? So your input is gonna be streams, and because we don't need to convert this to the feature or polyline, because it also can get the raster, okay? And also the output, so this is a raster or feature data that identifies cell or location to which the Euclidean distance is calculated. The output is going to be our names, okay? So what is the output? The output is going to be for each cell in the output, the Euclidean distance to the closest cell will be calculated, okay? So it's going to be the distance to this stream, okay? And what else? The cell size is like the digital elevation model. Everything is good, and then click OK. All right, so as you can see, so these are the distance to the streams or the channels, okay? So when you are closer to the stream, the distance is lower. When you are far from the streams, the distance is going to be higher. So that's the proximity to the streams or channels. All right, so we have all the information, right? We have elevation, slope, land use, land cover, precipitation, and then proximity to streams. So what is the next step? Let's only keep the stream distance to a stream layer or proximity to a stream. So we don't need the flow accumulation, we don't need flow direction, we don't need fill. We just want to have digital elevation model, we have proximity to streams, we need a slope, we need county, and then land cover and precipitation. So these were the factors that we needed, right? So for the counties, we just need to have the hollow and red color for the borders, okay? So this is these are the variables that we're going to focus on. So similar to the suitability analysis lab, we need to reclassify all layers, which makes them all unitless and ready for overlay analysis, okay? So we have to reclassify them into a common scale that 0 means not suitable, 2 means very low, 4 means low, 6 means medium, 8 means high, and 10 means very high suitability, okay? So the first one is digital elevation model, okay? So we have to reclassify digital elevation model. So if you select reclassify spatial analyst and focus on digital elevation model, click on classify. So we're gonna have 5 classes based on the natural break classification technique, and then click OK. So it is obvious that the flat areas are more at risk of flooding compared to the regions with higher elevation, right? So for the first one, so these are the flat areas, so it is the high risk area, okay? So we're gonna create the map of flood risk, okay? So here is gonna get the value of 10, which means that very high suitability for our floods, okay? And then 8, high, 6, 4, and 2, very low suitability for risk. And we're gonna also change missing values to no data, and the output is going to be reclass of digital elevation model. Anything else? And click OK. So let me turn all layer off. So here you can see that, so when you are closer to the lowland areas, closer to the lake, we have the highest suitability for flood, which kind of makes sense. And in these areas that are very high elevation, we have the lowest suitability for flood. All right, so the next one is a slope, and similar to a digital elevation model, flat areas or lower slopes are more flood prone because lower slopes increases the quantity of water soaked into soil, right? So lower elevation and lower slopes are more susceptible to floods. So again, from Reclassify, if you select Spatial Analyst, and then here based on the slope, I'm gonna reclassify it into, click on Classify, I'm gonna reclassify it into 5 categories based on natural break, but I'm not going to use the natural break. I'm going to use manual classification. I'm going to say less than 5, or sorry, less than 2 is the very high flood prone areas, right? So I'm gonna select 2. The next one is between 2 and 5 is high. Between 5 and 10 is gonna be medium. Between 10 and 20 is gonna be low, and above 20 is gonna be very low. Okay, so click OK. So between 0 and 2, flat areas are at the highest, very high risk, right? So this one gets the value of 10, then 8, 6, 4, and 2. And the output is going to be reclass underscore slope. And we want to change missing values to no data. Okay, click OK. So in terms of a slope, most part of the study area is like 10, gets the value of 10, which means that they are at very high risk of flood because it's kind of flat. So less than 2-degree slope. So the next one is precipitation, right? So again, if you go to the Reclassify, Spatial Analyst, and then Precipitation PRC, so we're going to classify into, based on natural break, 5 classes. And the output, so it is evident that the heavier precipitation intensity increases the chance of flood, right? So it is a no-brainer. So here it's going to be very low importance, right? So it gets the value of 2, and then gets the value of 4, 6, 8, and these areas with heavy precipitation gets the highest chance of flood, right? So or gets the highest score for flood. And then here I'm gonna call it the output as reclass PRC, precipitation, which includes rainfall, melting snows, and also ice, and so on. So click change missing values to no data, and then OK. All right, so the next one is land cover. And for land cover, it is obvious that urbanized areas are less vulnerable than wetland areas or rivers, right? So first of all, wetland areas, if you look at the legend of the land cover, so let me turn all layer off. For the land cover type, so the legend, the value that is 21, 22, 23, 24 are developed areas. So they are at the lowest risk of flood, right? So they get the value of 2, which means that very low risk of flood. So the way that it works is if you click on Reclassify, and then for the land cover. So for the land cover, you have to click on unique value because we're going to get all of the unique value. So 11 was open water and gets the highest value, which was 10. And 21, 22, 23, 24, according to the legend, are developed urbanized areas, right? So high intensity, low intensity, medium, and open space. So this these categories get the value of 2, very low chance for floods. 24, 31, 30, 41, 42, 43, 52, 71. So these are deciduous forest, evergreen, mixed forest, barren, grassland. So they are in very low, not very low, they are low chance or risk for floods. Okay, so they get the value of 4. So 31 is going to be 4, 41 same, 41, 42, 43, 52, and 70. Oops, 52 and 71, they get the value of 4. So 81 and 82 are planted or cultivated crops, so they get the value of 6. And 90 and 95 are wetland areas, and they are at high risk of flood, so they get the value of 8. All right, so this is how we can reclassify the raster. And after that, so let me check. The first one gets the value of 10, 2, 2, 2, 4, 6, 8, and 8. All right, so this is going to be a reclass underscore Landcover, and change the missing value to no data, and then OK. All right, so the last one is proximity to streams or channels. And again, it is obvious that the closer distance to the streams, the higher probability for flood, right? So if you go to the Reclassify Spatial Analysis, so proximity, distance to the streams, and here click on Classify. We're gonna classify it into 5 categories based on natural break, and then click OK. So the closer gets the highest value. So it's going to be 10, and then 8, and then 6, 4, and finally 2. And after that, so this is going to be reclass underscore stream or str, okay, and change missing values to no data, and then click OK. All right, so now we have reclassified all layers, which means all layers are unitless and they have been rated or scored. So the next step is that we have to combine these reclassified layers based on the weights, based on the given weights, based on the opinion of the experts that here we mentioned. Elevation has 10%, slope 15%, 10% for land cover. Precipitation is the most important one, and proximity to a stream is going to be 30%. Okay, so how we can combine these layers? So this is based on the reclassified factors. After you prepare all of the factors, reclassify them, which means that you rate them, you make them unitless. The next step is that we have to combine them based on the given weights according to the opinion of the experts. So, and again, you can use a raster calculator that we did that for the last time, or another way or more user-friendly way is to use weighted sum function. So if you type weighted sum, and here you can directly give each raster the weights. Okay, so for example, we had reclass for precipitation, we had reclass for streams or distance to the streams, then we had so let me remove this one. Reclass for slope, then reclass for digital elevation model, and finally reclass for land cover, right? So for the precipitation was 35%. So let me see, the total has to be 100. 35, 30, 65, 75, 85, 90, and 100. So here is going to be 35%, 0.35, and reclass for distance to the streams is 30%. Reclass slope is 15%, and the last two are 10%, right? If you add them up, the total is going to be 35, 65, 75 plus 5 is 80, and 90 and 100%. And so this is going to be your final flood risk map. Okay, flood underscore risk, and then click OK. So this is, let me uncheck all layer, turn all layer off, and flood risk. So here we can see that in the in the eastern part of the study area, we have higher chance of flood, because also here we had the higher precipitation, if you remember. So here, the chance of precipitation, because precipitation was the most important factor. That's why here in these areas, compared to the western part that had the lower precipitation, so it kind of makes sense because the precipitation was the most important factor. And so that's how we can create a risk map for the flood. However, in the future, it would be okay to consider some other factors like soil type like vegetation cover, like for example, normal difference vegetation index, NDVI, that we will obtain that from satellite images in the future labs. So you can also reclassify this flood risk map. So let me reclassify it. So I'm gonna reclassify this flood risk into 5 classes based on the natural break. So the values are, so as you can see, the values are starts from 3 to 10. So which is like 3% of the chance of the flooding, or 30%. Here is 96% compared to the other areas. So click OK. So here the value 1 means low chance of flooding. 2 means, so this one is very low, low, medium, high, and very high. Okay. So here it's going to be your reclass underscore risk. Okay. And then OK. So here is going to be your the chance of flood. Okay, so let me change the symbology, use a better color. Okay, so in these areas we have higher chance of flood compared to these areas, because here we gave higher weight, because here we had higher precipitation, and precipitation was the most important factor according to the opinion of the experts compared to the others. So depending on the weights that you give to the layer, you will have different layer, different risk map, and also it depends on the months of the precipitation. Final thing is that you can create, so if you go to the layout view, so here you can create the risk map. You can add the, so for example, you can add the title, you can add the legend, what this color indicates. You can add the north zero scale bar, your name, date, and after that export it as a JPEG file.